Dear student, good morning, very good morning to each and everybody. And today we are going to discuss about the 2D NMR spectroscopy. I'm going to give you a flavor of 2D NMR spectroscopy. Fine details will take a lot of time and which requires a lot of few more classes. And as we don't have that much time, so I confine myself to one lecture to give you a general idea or broad idea about the 2D NMR spectroscopy. Before going to the 2D NMR spectroscopy, let me tell you why we need a 2D NMR spectroscopy. And we need 2D NMR spectroscopy because there are certain drawbacks or certain limitations are there with the 1D NMR spectroscopy, which we have learned so far. Now, let me ask you at this point of time, what exactly is a 1D, 2D? Can anybody guess answer for this? Can anybody answer what do you mean by 1D, 2D? Anyone? You remember the NMR spectrum is a two-dimensional plot. Whatever we have learned so far, it is a two-dimensional plot. It is the x-axis is the chemical shift, right? Frequency square, frequency scale, and also the y-axis is the intensity. Am I right? It has two dimensions. Do you agree or not? It has two dimensions, right? But still, even though it has two dimensions, we still call it as a one dimension because it has only one chemical shift value. I mean, in the x-axis is only having the chemical shift, that is the frequency scale, and y-axis is the intensity. Since there is only one frequency scale, okay, then we call whatever we have learned so far, it is said to be the one-dimensional NMR spectroscopy. Okay, and two-dimension means that the two-dimension, there are two chemical shift scales will be there. Instead of one, there will be two chemical shift scales will be there. That means the y-axis and x-axis both are going to be our frequency scales. So that's the difference. If I say it is a three-dimension in the NMR spectroscopy, then you have to understand that they are going to be three chemical shift values or scales or axes. Okay, so three-dimensional chemical shift values are somewhat very much familiar in the clinical diagnosis. That is the MRI imaging, right? So there the scanning is done based on the chemical shift values. So there are there are three resonance frequency resonances are basically recorded continuously based on the water, and then the image is generated. So that is a three-dimensional thing. But what we are going to discuss today is the two-dimensional. And remember that the two-dimension refers to the two chemical shift scales. Okay, so the x-axis and the y-axis of our NMR spectrum is going to have two chemical shift, right? So that is what I mean by two-dimension. Okay, in the case of one dimension, only one chemical shift we have seen so far. Okay, so that's the brief note on the one dimension, two dimension. Then let us go to the discussion of what are the limitations of 1D NMR. Only when you understand, these things, then you will appreciate the two-dimensional NMR spectroscopy, right? One of the major problem with the one-dimensional NMR spectroscopy is this. The first point, the correlation information is absent. What do I mean by the correlation? You take any NMR spectrum, that how one nuclei is basically connected with the adjacent nuclei is totally absent. So we can't find any correlation. The correlation means the connecting information, how a nuclei is connected with another nuclei. Okay, The connectivity information, what we technically call it as a correlation, is totally absent. We can't see in the one-dimensional NMR spectroscopy. Of course, from the splitting, we will come to know that okay, there is somebody is there. We are just guessing. Okay, just that is a problem with that is a major problem with the one-dimensional information. And you just imagine a molecule. Let's say we have a ethanol, and we have a propanol, and we have a butanol, and we have a pentanol, right? And we have some other, hexanol. Let's say. Why I'm saying all these molecules? Just imagine what will be the chemical shift values of the methylene and methyl groups in these alcohols. They all basically complex. They all will resonate at one place, right? Methylenes and then methyl groups, the terminal methyl groups. They will resonate more or less at one place, right? Now, as the size of the molecule is increasing, okay, from ethanol to hexanol, the complexity basically increases at certain region in the NMR. Am I right or wrong? You just imagine where a methylene will give. A methylene, which is adjacent to the oxygen atom in the case of simple ethanol, where it gives, it is 3.5, right, roughly. Then the same methylene, adjacent to that methylene, where it will be somewhere around 2, okay. Then when you go to the next one, where it will be somewhere around 1, right? Okay, so that is the case of a simple, and then methyl will be 1, right? So if you take a butanol, that is the case. And if you take a pentanol, okay, so all the peaks basically are going to resonate at a small region. So that is something that makes the spectrum very complicated. Okay, therefore, that is one thing. The complexity. Okay? The complexity increases as the size of the molecule increases. That is a very much established concept, which doesn't require any kind of explanation. And even if you think of a small drug molecule, which is having the molecular size of maybe 300 to 400 molecular mass, and then imagine a small peptide, and imagine a small protein. Okay, so we have so many methyl groups, methylene groups, and H groups. Okay, methine groups. So there are so many things. As the size of the molecule increases, uh, irrespective of the molecule, category of the molecule, the NMR spectrum basically going to be very much complicated, right? So that complexity, it cannot be addressed in the one-dimensional NMR. It is totally impossible, because all the peaks. So far, we have seen nice resolved NMR lines, right? NMR peaks. For example, ethanol, if you take, we have a nice triplet, then when nice signals are there, doublet, and then all those things are there. Okay, these are very nice signals. But what I'm trying to say is that suppose if you have a bigger molecule, they all comes together, they resonate, and then you don't see these well separated peaks. Everything will be very complicated. Okay, so how to understand the information which is basically present in a small region, within a small region. Okay, that is not possible with one view, but if you can record simultaneously two chemical shift values of the same molecule using a different technique, it is fairly easy to understand the correlation information and also interpreting the peaks and then therefore the molecular structure of the unknown compound. So those are the limitations, and these limitations will be addressed by the two dimension. The third point is another drawback or limitation of the one-dimensional spectroscopy. So when you shine the radio frequency, and basically there are multiple nuclei are there, and all these nuclei basically they what we call it as a quantum coherence. So all these nuclei will be showing the coherence. Okay, and this coherence information, it's not the hydrogen hydrogen coherence, but then it can be a hydrogen carbon hydrogen nitrogen and various other inter coherence are generally generated. So when you are shining the radio frequency pulse, so these coherences cannot be seen in the one-dimensional spectroscopy. This is possible only if you basically record the two-dimensional or the higher dimensional NMR spectroscopy. Okay, let me go back and somebody would like to join. It looks like, yeah, Sri Lanka. So that is what. Well, these are the three drawbacks of the one-dimensional spectroscopy. The typical one-dimensional spectroscopy, NMR spectroscopy, doesn't give you the correlation information. For your kind information, correlation is nothing but the connectivity. How a particular nuclei is connected to another nuclei in the molecule, that is totally absent. So another one, the complexity. As the size of the molecular, as the molecular size increases, then we have so many protons and we have so many carbons, we have so many nitrogens, etc. in the molecular. That basically makes the complexity and difficult to interpret the NMR spectrum, and from there to the molecular structure. So we need another thing is that multiple coherences are generated, but then these coherences information, how they are correlating with each other when you excite the molecule with RF pulse, cannot be understood. Okay, and this is something that I have given one molecule. So these are the major three drawbacks. Okay, and here there is one small molecule I have given isopropyl methyl ketone. Just imagine that this methyl, where it will give. Okay, so it has a it is basically a septet, right? And then these two methyl will be a doublet and this will be a singlet. Okay, so there are three peaks are generated, but what I'm trying to explain this point, correlation. How these are connected is not known. What you will get is a septet. Okay, there is basically a bunch of peaks. Okay, that is one thing for this methane proton, right? A bunch of protons will be seen septet. Then there is a methyl thing will be there somewhere. This methyl is a doublet. That doublet will be there, and then this methyl is a singlet, and this will be there. Okay. Now in this spectroscopy, that let's say this is around maybe one. This is maybe 1.2. This is one. Let's say. Okay, and this is the maybe at a 2 or so something like that. Okay, so now how these you have a 1, 2, 3. So from this information, you don't know how the nuclei are basically interconnected. This information I know. What you know from the splitting pattern is something that okay, I have two neighbors. That's all. That's all you know. But otherwise, you don't know. Okay. This, since this is a simple molecule, then you can easily say, sir, I from the splitting pattern and from the logical background what we have so far, I can interpret. Fine, but you just imagine that if it is a bigger molecule and you have so many methylene, so many methane, so many uh, methyl groups. So if all the things will resonate at one place, that makes the complexity. That's what I'm trying to stress. Okay, so this to understand, I will give you a brief idea how this is generally done. Okay, so a simple two-dimensional NMR spectrum spectroscopy, how it is done with regard to the homonuclear COSY spectrum. I will explain, and rest of the things probably you can read if you are interested. But in the examination point of view, I will confine my questions only to the correlation spectroscopy. Okay, so just to give you a flavor, this already we have discussed what exactly the technique that is being followed to record a one-dimensional NMR spectrum. Okay, in a one-dimensional NMR spectroscopy, we just prepare the molecule and then we apply a 90-degree pulse and then we detect it. As a result of which we get a NMR spectrum. Okay, this is the null NMR spectrum. So this is a simple concept, a simple procedure that is generally routinely followed to record the one-dimensional NMR spectroscopy spectrum of any molecule. Okay, this is a proton, but then you can record any magnetically active thing, one-dimensional spectrum in this manner. The process, the two processes are there. First, you are preparing the sample for it, and then you are basically exciting. The preparation involves the excitation using the placing in the magnet. The sample is being placed in the magnet, and then also applying the radio frequency pulse, 90-degree pulse. And just after that, we switch off the pulse, and then it will be decaying. Okay, recording is nothing but the detection is nothing but the recording the FID, induction decay. Okay, and once you detect that FID is processed, and you will get the this spectrum. Okay, this spectral information we try to understand and interpret to the appropriate molecular structure. That is what generally done in the NMR. However, in the case of a two-dimensional experiment, it is slightly different and slightly complicated also. But there are four uh, methods or the steps are involved in the 2D NMR experiment. The first and foremost thing is the preparation. This preparation is exactly same as the preparation in the one-dimensional NMR spectral measurement. Okay, so initially the spins are basically in the relaxed state; they will be excited. Okay, that is one thing. Then later on, the chemical shift and the spin couplings evolve. That is the evolution. Okay, and then there is another process. It is called the mixing. Okay, the second RF pulse is also applied to create the observable transverse magnetization. Okay, and the final step is the detection. Okay, so there are four steps broadly involved in the two-dimensional NMR spectroscopy. One is preparation, evolution, mixing, and detection. These are the three. So evolution is generally it evolved the magnetization vector evolved with the times. Okay, or the individual magnets are basically evolving with the time. That is the T1, and then the detection, that is also another the time thing. So there are two time informations. Please remember and recall that. That means basically in the two dimension we will have two FID, not one FID. So we'll have two FID, and these two FIDs are processed, and then they will be processed through the Fourier transform. Therefore, we will get the two frequency data, or and then two frequency data means two chemical shift values. Okay, that's the general description, and little more on that. You can just see the. So we will record a series of FIDs. Okay, we will record a series of FIDs in the two-dimensional NMR spectroscopy measurement, and then we process that information through the Fourier transform. The Fourier transformation we can do with respect to x-axis as well as the y-axis. As a result, we will be getting some kind of contour plot. So we'll be the two-dimensional NMR plot is represented in a contour diagram, contour plots, where it will have a dots. Okay, a thicker dot, a thinner dot, simple point. So these are the broadly these are the steps followed in the two-dimensional NMR spectroscopy. And little more on that, if you want to learn, in the NMR first 1D NMR. So this is what I already explained, that we will apply RF pulse of roughly about 1 to 10 nanoseconds, and then immediately the FID starts, and then the pulse is applied only about this, and then we'll stop. So just after stopping the pulse, then the acquisition, the magnets which are excited, basically they relax back to the ground state. That is something it is being collected for about 1 to 10 seconds. 1 to 10 seconds, okay, so that the acquisition will take place. FID will be recorded. Then this FID, we will try to process it and we'll get the spectrum. Whereas in the case of two-dimensional number spectroscopy, so this is what exactly happens. Okay, we will apply two pulse. Okay, you can see here that the first is the 90-degree pulse. Okay, after applying the 90-degree pulse, immediately after that you can apply another 90-degree pulse, and then you can record the FID. Okay, this is one method. And then, instead of applying the second 90-degree pulse, what we do, we just give a slight delay. The delay can be 1 second. Okay, you just you have applied 90-degree pulse for an about 10 or 12 microsecond, and then you just give 1 second gap and then apply another pulse, another 90-degree pulse. Okay, and then again you record the FID. In the next experiment, okay, initially you give 1 second, then later on you can give a 5 second or 2 second. The time is basically your choice. Okay, you can give the choice of yours, you can choose the time of your choice, and then you again record the FID. Okay, so the pulses, okay, so there is so what we are doing basically, with the time, one time is there in between applying the two pulses. Okay, so this time which is present in the two pulses can be varied such that, okay, it can be varied based on our choice, and then you can record the FID in the usual way. Okay, and if you this is what exactly represented here. So you can notice here the delay is almost close, it is 0 here. Okay, but then here it is a more gap. That means that more more delay is given, and this is the delay is given from the one pulse to the other pulse. So this is a time information, right? This is probably you can T0, and this is a T1, right? And this is T2, and so on. So and so on, you can continue. Okay, and when it comes to the processing, this is one FID, right? This FID is exactly similar to that of a simple one-dimensional FID. Okay, so this FID, if you process, you will get the spectrum, right? Right. This is what it is done here. The Fourier transform is done with respect to this axis, okay, in one case, and then later on this axis, both cases. Okay, why? Because you have two time information. Okay, one is the usual FID time, recording the FID time, that is 10 seconds, 1 to 10 seconds, the acquisition time. Okay, so this actually T2. Okay, but then there is a delay that we are giving from one pulse to from the one pulse to the other pulse. So that also another time. So with respect to that one, if you can do a Fourier transformation, that is the y-axis, then what you obtain is this. What you obtain is this contour diagram. Okay, so if you see in the 3 dimension, the contour diagram appears like this. So there will be spots. Okay, you will have a spikes. You will have a spikes. Okay, and the spikes in a simple two-dimensional graph is represented in this manner. Okay, the spikes. These are the three-dimensional representation. Okay, but then in the two-dimensional, simple graph, we can represent the same information like this. Okay, so what do I mean by these are these are each one represent. This is called contour diagram, and this contour diagram has a contour peaks, and each one basically is represented with the thick and thinner things. The more the thick is, if I draw something very thick, okay, here, let's say, and then outside I just draw something like this. Okay, that means this is where the position, the peak is having more intensity. If I write a thinner, less dark peaks, then we say it is a less intensity. So the intensity, the third dimension, is represented with a dark and the light dark. Okay, so that is the way it is generally represented. Okay, the same information that you have a series of, these are basically three-dimensional representation. So after the, just after recording the NMR, two-dimensional NMR, just after the two-dimensional uh, NMR measurement, that you will have a, so many FIDs are there, okay, which are recorded at different time scales, which are recorded at different time scales. So with regard to usual FID, with regard to the usual FID. So with regard to this one, if you process it, you will get some kind of spikes. Okay. Then again, that one, if you process, you will get this type of peaks. Okay. If you process, you will be getting this kind of thing. Okay. The Fourier transformation can be done initially with regard to T1, then later on T2, or else with regard to T2 and then later on by T1. So either way, you are going to get the same diagram. That is nothing but this type of three-dimensional surface. This surface is a bit difficult to understand in a normal routine case. Therefore, it is represented in this manner. It's a contour diagram. So which will have a peaks. Okay, this will have peaks, and these peaks are broadly classified into two. One is the diagonal peaks. The other peaks, what we call as off diagonal peaks. This is called off diagonal. This is also called off diagonal. And these, with respect to the diagonal peaks, these off diagonal peaks are very much symmetric to each other. Okay, very much symmetric to each other. And these off diagonal peaks are also referred to as the cross peaks. Cross peaks. Okay, the cross peaks will give you the information of, maybe let us look at the some kind of spectra so that you will understand. Yeah, so this is what we get. This is a typical representation of a two-dimensional NMR spectrum of any compound. Uh, you can see here that this is one frequency, that the typical, our typical scale, there is delta. Okay, this is one delta in ppm. This increases like this. Okay, there is another scale. There is another scale on the y-axis. Okay, this will increase like this, delta 2. Okay, this is, or this is delta 2, you can take it, because that's the way we have. This is delta 1. So the frequency scales are there, and the very interesting thing that the one-dimensional NMR spectrum of the same compounds are represented on the other side. So this is the one-dimensional NMR spectrum of the compound. Okay, this is also one-dimensional spectrum of the compound. Okay, its scale is exactly this. Okay, of course you can make it out, right? This is the scale exactly same to this, and this scale is exactly same to this. Okay, so the one-dimensional NMR spectrum of the same compound is represented on the other vertically and horizontally, and you will have a scales, like the typical scales are represented from the 0 to 12, whatever it is. Okay, or 0 to 15, 0 to 20, depends upon your peak availability. So up to that, it will be shown, the scale will be shown. And in the case of homonuclear, we will have a same scales. But then if you are really interested to look at the correlation between the carbon and proton, that we call it as a heteronuclear correlation, then in that case, one scale will be proton delta scale, the uh, other one will be the carbon NMR scale. That you know that the carbon NMR scale can go up to 250, right? From 0 to 250, whereas the proton will go up to 0 to 15 or 16. Depends upon the situation, right? So this is the general introduction, and these peak, what we call it as off diagonal or cross peaks. Okay, these two are cross peaks, and then these A and B are said to be the diagonal peaks, and the diagonal peak positions exactly, you can see wherever you have a one-dimensional peak, there you will see a contour peak. Okay, so the diagonal peaks, wherever you see, so those are exactly matching with the peak positions of the one-dimensional NMR spectrum. But half diagonal is something which is more interesting as far as the two-dimensional NMR spectroscopy is concerned. Okay, so with this brief introduction, let me go and explain about the correlation spectroscopy of the one propanol. This is the simplest example to understand. It is very easy. Therefore, I picked up this example to explain the concept of two-dimensional NMR spectrum. So you can see here there are the okay. You can see here in the diagonal how many 1, 2, 3, and 4. Can you see this? And the fourth one is the proton that actually came from the the proton from the alcohol. Therefore, this is less intense. Only one proton of that kind is there. Therefore, it is shown very small area. Okay. Whereas in this case, you can see it is occupying more space, and this is thicker peak, and this is even more thicker. Okay, this is exactly matching with this third one. Okay, there are four diagonal peaks, and the four diagonal peaks you just draw a grid line to the this axis. Okay, so this is something that we are trying to understand. This is the first scale. This is one delta scale. Okay, this delta scale we are trying to understand, and you have one peak here. Therefore, one diagonal peak is there. You have another peak, one diagonal peak. You have another peak, another diagonal. So corresponding to each peak in the one-dimensional spectrum, you will have a diagonal. Those many diagonal peaks are there. Now, what is interesting in two-dimensional NMR? Now, as I said about the differences between 1D and 2D, here you don't know how this peak, this peak is correlated or not. You don't know whether these two are correlated or not. You don't know these two are correlated or not. I mean, correlated means connected or not. Okay, so this information we can't understand from the simple one-dimensional spectroscopy. That is why we have recorded the two-dimensional NMR spectrum. Now you can see, you take any two peaks, any two diagonal peaks, and then see is there any cross peak is there or not. If there is a cross peak, then we say there is a correlation. Otherwise, we say there is no correlation. Right? You can see here that this is 1 and 2 I am taking. Okay, these two peaks I am taking, and there is a cross peak. Just draw one line here, and then you can see here there is a nice correlation. So these two 1 and 2 there is a correlation. So there is a nice correlation between 1 and 2. Okay. So 1, 2, 3, and 4. Okay. So this 1 and 2 there is a correlation. That's why we are saying that because there is a cross peak. Okay, one is having correlation with the other one. And then what about this 3? 3 and 1, you just take it. Is there any correlation? Because here when you draw a vertical line, you don't see any peak, right, which is correlating with either this or this. On the top of third peak, you don't have any other peak, right? You can see here above, you don't have. Okay, what about the fourth peak? Fourth peak is having another cross peak. Fourth one, this is the fourth one. I don't understand. What is the stupidity? Yeah, the fourth one, you have this is the fourth peak. You have a diagonal peak. Okay, so just you draw the vertical line above to that one, and then you see that this is having two. So this we labeled as a second peak. So this fourth one and then this second one both are correlated, right? So whenever we see a correlation or whenever there is a connection, then we will have a corresponding or diagonal peak. Okay, so this information is very much important in assigning the task. How it is important? since it is a propanol, you will not appreciate this discussion very much. But then when you go to the higher molecular size molecule where you have a lot of overlap between the NMR peaks, and this kind of information is very useful, and very with no time you can interpret the data. Okay. Now you can easily say that what is this? Since it is a propanol, that you have the molecular structure of this kind, right? CH3, CH2, and then CH2, and then OH. So this is the simple. This is the molecule. This is the chemical formula of the one propanol, and then this one. Let's say if you say it is 1, and this is 2, and this is 3, and this is 4. Okay, so this is how the peaks are probably arranged. Okay, this is 1. The one peak. Sorry, I think let me label also. This is 1. This is 2. This is 3 and 4. Okay, and we know, since the chemical formula is known, then easily we can interpret. Now the third one, where is that one? So this is directly connected to OH, and this and has a two protons are there on the edges, and therefore this will be a triplet. So this peak is correspond to this one. So it has only one correlation. It has only one correlation, and therefore corresponding thing you can see here. It is connected. 2 and 3 are connected. So that is the information that we are getting here. Okay. So what is this peak? This is the last peak. The last peak is this, and it is connected with what? It is connected with this one. Okay, this CH2, second CH2, second methylene proton, and this is exactly matching here. Okay, methylene, you can see here that how many splitted line you can expect here. Then you can see here it is a sextet. There are 5 neighboring protons are there. Therefore, it will be seen as a sextet. You can see here. Okay, so it is having a correlation with this and with this proton. Therefore, we will see that, and that is why that we are seeing this off diagonal peak. Okay, what about this? What about this? This one is basically from this methylene, right? That is very clear, right? This peak correspond to this methylene. Okay, the second proton. Then you can see here there is a off diagonal peak and off diagonal peak. This off diagonal peak, actually it is correlating with the adjacent methyl, this methyl. Okay, so this is having this one, and then you can draw a horizontal line to this chemical receptor value, and this exactly matching with this particular methyl proton, right? So this is how that we will understand. In the case of propanol, it's very straightforward and easy to interpret the data, but as you move on, then it becomes very cumbersome job. And this is the ethyl acetate. You can see here that this has only one correlation between 1 and 2 protons. Therefore, we will see only one off diagonal peak. Okay, and then I forgot to tell you that you can proceed. You can explain this. As I said, it is actually a symmetric one with respect to the diagonal line. It is a symmetric one, and you can also use the same strategy. You can either you take the upper half or the left hand side half or the right hand side half to explain the concept. And what about these things? These are very much symmetric, so you need not to worry about this one. So this is a symmetrical information. This is a symmetric with respect to the diagonal line. So this information, either you can use the spots cross peak which are this side or which are that side. So you need not to take both. Only one information you can take it and interpret the data. That is sufficient. Okay, and this is again the same concept, that it has a total 3 protons are there. This methyl, and then methylene, another methyl proton. So 3 peaks are there. Therefore, 3 diagonal spots you can see here, and then but then we will have only one correlation. So 1 and 2 only is having correlation. Therefore, this 1 and 2, basically you have a up diagonal or cross peak is same. Okay. And what about this is a glutamic acid? This is a glutamic acid, and we have confined to only to this, not to the acid protons. Not to the acid protons are not shown here. Then because that scale will go up to 12 or 13, therefore it is not shown here. But then the aliphatic region, mostly the aliphatic region, is shown here in this cozy spectrum, spectroscopy. Okay, here you can notice here the aliphatic means these are the three, and then this is another one. So NH2 protons, as I told you, it is a level proton, very difficult to get. It will be a very broad one, and I think they have not taken any precaution to get the primary proton. So let us not worry about the labile proton, this one, and also these acid protons. But other, there are how many protons are there? There are three. Okay, this is having a correlation with this. Okay, so 2 and 3 protons, carbon protons are having correlation, and then similarly 3 and 4. Right. So this information is reflected exactly in this thing. Okay, so this one is having a correlation with this one. Okay, similarly this diagonal peak is having a correlation with this one. Okay, so that means what is this? This is having a correlation, right? So this basically the third one, both sides is the center one. That is why that two diagonal peaks are basically matching. Here, okay, here this is the third one. If you can just focus, this is the third one. So this is having one diagonal peak, and which is actually on the same line, same horizontal line. There is another half diagonal peak to another one. Okay, so this is a third one, and this probably is the CH methane thing is shown here, which is having a correlation with the third one. So third one is this one. Okay, so this how we can go on discussing this type of things in many spectra, many things. This is a simple ethyl benzene, just to give a flavor that aromatic protons are here, and then aromatic protons are there is no connectivity between the aromatic and aliphatic. Therefore, there are no off diagonal peaks. But aliphatic, you have a methylene and then methyl. So both are mutually connected. So mutually connected, and there is a J coupling between them. Therefore, we have one correlation. They are correlated because you can see one off diagonal peak or cross peak. Okay, so this information, this type of information, we can continue in explaining to. This is a 2-butenoate, ethyl butenoate, and here also you can follow in the similar manner in discussing all these things. You have A and B, and there is another P. So all these P's can be explained. Okay, you can just draw an off diagonal peak, and then see how many. Sorry, you can draw a line on the diagonal peaks. You connect all the diagonal peaks. Okay, and you take either upper portion or lower portion to explain this two-dimensional, any two-dimensional NMR vector. Just to concentrate on the peaks, and then you draw horizontal or vertical line, and then see how they are connected. See how they are connecting. So where they are meeting, wherever they are meeting, if there is a spot, okay, if there is a intersection, then definitely at the intersection point, if there is a peak, then that means there is a correlation. That means they are basically connected with each other. So that is the information primarily we get from this. Similarly, you can see this peak above, there is a peak, right? And this is matching with this. So therefore, I can say easily that this and this both are interconnected. So, and similarly, this one, above this peak, there is a B peak, which is matching with this one. Therefore, this one and then this one, both are interconnected, right? So uh, this is something like, how they are connected. Uh, This I can give you a small analogy. For example, uh, you can just take one name, any name. For example, you can take Ravi Kumar. Okay, my name is Ravi Kumar. Okay, and suppose you are trying to search my name in your phone book. Okay, any one of you, you are trying to find out Ravi Kumar, my contact number, for example. Initially, okay, you only give the keyword Ravi. You start writing Ravi. You will get few contacts. Okay, and later on, you use another keyword, only the Kumar. Only Kumar you can just use it. You will get with all Kumar, you will get a list of numbers. Okay, neither those list nor this list is correct, but your answer is there in those one of both list. So one of the both list will have uh, one of the answer is correct with Ravi Kumar. Okay, but later on if you try, there is with Ravi Kumar with the exact name, then you can find really the exact contact number of mine, right? So that means only when there is a correlation, I mean, only when there is an exact correlation, that means you are trying to search my name with my correct name. Therefore, you got the exactly only one contact. You don't get any other contact. Am I right? When you search exactly Ravi Kumar, then you will get the only one contact. But if you try only with the Ravi or with the Kumar, you don't get the exact contact number of mine. Instead, you will get a list of contacts, right? So this is what exactly happens in the two-dimensional thing. This is just a illustrative example. Okay, so if there is a connection, if there is a connection between any two neighboring protons, then we will see off diagonal peaks. Those off diagonal peaks, from the off diagonal peak, it is easy to interpret uh, derive the molecular structure. Okay, so these are all things, and then this epsilon is there in the Silverstein book. I must recommend all of you to go through the epsilon. It is somewhat complicated, but very easy to interpret the data. So this entire explanation of the epsilon is available in the Silverstein textbook. It may be asked in the it may be asked in the examination point of examination. So you read these things, okay, how they are correlated. So there are, it looks very complicated, but don't worry. What you do is just draw the diagonal line and then label your peaks and then assign those things with this way, and then try to later on you draw the horizontal line and vertical lines and then match with the other peaks on the other axis. Okay, so this is having you just horizontal line and then vertical line. So with what it is matching. So you can see here. So the in this explanation, the lower part of the left hand side of diagonal peaks are utilized to interpret the spectrum. You can draw the horizontal line here, and then now you start drawing the vertical line. So when you start drawing vertical line with this, it is matching. Okay, and similarly here it is matching. Similarly here it is matching. That means each matching, so there is a correlation. Each matching we say it is a correlation. So that information is very much appreciated. So with this background, let me give you what exactly is the information people are trying to understand from the two-dimensional NMR experiments. So let's say you have a carbohydrate of like this, and then you can actually right now what I said was what we say it is a homonuclear correlation spectroscopy. How they are correlated? They are correlated through bond. They are basically correlated, and then the J coupling is there. So that is the information that we utilized. Okay, and a simple COSY is nothing but the correlation spectroscopy. So J coupling. Okay, J coupling. For example, you can see here the red labeled protons, red labeled proton, how they are connected with each other. it can be understood from the by recording the correlation spectrum. So since both nuclei are from the protons, then we say it is a uh, homonuclear correlation spectroscopy. In shorthand notation, it is COSY. And you can also look at the correlation between a carbon and another carbon. That is also homonuclear correlation spectrum. Okay, so homonuclear. Homo means the same nuclei. Homo means same nuclei. So either carbon or photons. Then total correlation. What do you mean? This is called toxic. These are the few abbreviations are there. Toxic, TO, CSI, toxic, total correlation spectroscopy. Now, what I'm saying, it is, you see that the protons in the six-membered this ring, how each proton, they are connected with each other. So that correlation, if anybody wants to find out, it is possible by recording the two-dimensional spectrum. It is possible to do that. So that we call the total correlation. The previous one is confined to unit 2. Now, in the total correlation, in a given entity, how if you are considering all the same nuclei, it is the total correlation spectroscopy. Now, in the ring, you have different protons are there, methyl protons, methylene protons, okay, axial, equatorial, different locations, you have different protons are there. So all those things, if you are considering, all the correlations if you are considering, that is called total correlation spectroscopy. Okay, and you can see here this region. This region you have, if you are considering, that is the total correlation of that one. Okay, that is one thing. Okay, so that is also a total correlation, but the network is different. Okay, and then the heteronuclear single bond quantum correlation. That means you can see here that heteronuclear, it is not from the same nuclear. First thing, it is not. It is from the different nuclear. A carbon, proton, the nitrogen and proton, like this. Okay, so this is the heteronuclear correlation. How they are connected? Through bond. How they are connected? Through bond. Such a information can be obtained. Such a two-dimensional plot, the contour diagram plot can be obtained by recording the spectrum. Okay, that is a heteronuclear single quantum correlation. Single quantum means that you are both are from the different one, but you are only considering one heteronuclear, not many. Okay, so heteronuclear multiple bond correlation. Okay, it is okay if you are considering if you are considering two different nuclei which are connected by more than two bonds or three bonds, then we say it is a heteronuclear multiple bond correlation. That means here you can see here there is a proton and there is a CH carbon. So this correlation, they are separated by two bonds. So this correlation you are seeing it. Okay, it is not a single bond. Okay, previous one is a single bond which are connected by C and H, N and H. But here now you can see they are correlated by more than one. Then noisy is the nuclear Overhauser effect spectroscopy, and noisy rotating frame Overhauser effect spectroscopy. I told you in the last class about the nuclear Overhauser effect. Nuclear Overhauser effect actually is because of the dipole-dipole interaction which is happening through space. Okay, if the two nuclei uh, through space, if they are separated within the 5 angstroms, then the dipole-dipole spin transfer takes place, as a result of which the peak intensity either getting increased or reducing depending upon the situation, right? So that concept you can make use of it, and then you can uh, have the two-dimensional plot. Okay, and that is a what we call it as a noisy nuclear Overhauser effect spectroscopy. Noisy, that means through space how two different basically nuclei are connected with each other, that information we can get it. Okay. Yeah. So this is the explanation what I have said. I mean, this is the uh, COSY spectrum of this particular molecule and its interpretation. It is already explained to you. There is nothing. Just with the animation again, I'm showing. So this proton to the diagonal peak is here. Okay, and this peak is correspond to this one. And then there is another one you can choose in the diagonal peak. You can choose any diagonal peak, any two diagonal peak spots, and then try to see a correlation or not. As you can see here, you just upload here, go vertically, and then look at here. There is something. So therefore, that means both are correlated. Similarly, you go here, go. There is a one more diagonal peak, and then you draw the horizontal line here. If you draw here, there is another peak. That means this one, okay, and this one, both are correlated, right? And similarly, these and this, both are correlated. That is why we see diagonal peaks. So this kind of interpretation can be extended to further and further to illustrate the molecular structure. Okay. So mostly we come across in the two-dimensional spectroscopy in the organic chemistry is this COSY and the HETCOR. COSY means the correlation spectroscopy, where homonuclear correlation is only applicable to the homonuclear correlation. That means either protons alone or the carbons. So that is the correlation. Of course, it can be a total correlation or it can be a correlation of two nuclei. Okay, that is the thing. And then head core is very interesting. It is again a correlation spectroscopy, but then it is from the different one. This is again very useful technique to deduce the connectivity information. Okay, you recorded for example, you recorded a carbon NMR spectrum of some molecule. Okay, it will give you some peak. Okay, it will give you the corresponding carbon peaks. Now, how these carbons are connected with the protons? With the protons, if you want that information, Hecker is a beautiful technique. Okay, in that Hecker plot, what you obtain is this. Okay, you will get here. This will be your proton scale, proton delta scale, but then this will be your 13C. Okay, this is very useful. So you will get peaks. Okay, and then if you see a correlation peak here, then you say that these two carbon, a carbon and this is a proton, this proton and this carbon, there is a correlation. That is why you see a you can see here. Suppose if you see a up diagonal peak here, then this is matching with this carbon. So just extrapolate here. This is the carbon peak. Okay, that means that carbon and that proton are related. Okay, so this is a very beautiful technique to immediately arrive at conclusions about the carbon and proton connectivity. Right. Similarly, is the case for carbon and the nitrogen and proton, and similarly is the case for any other two different nuclei. Okay, HETCAR is another very interesting technique. In the same manner, we follow. And if you want the HETCAR spectrum, I have one HETCAR spectrum here. This is the ethyl 2-butene butanoate, and you can see here the y-axis is the and the x-axis is the simple proton NMR spectrum of the same 2-butene, that, and then this is the carbon. You can see here the scale is going from 0 to maybe 170. It is given, right? And here very interesting point that we can get, that the connectivity is something that is very useful. You can see here there is a one peak. Okay, so this carbon is connected with this one. Okay, this carbon is connected with this one. Okay, so that is why you see a nice So this peak, you draw the horizontal and vertical line and see at the intersection, if there is a peak, then we say it is a both are connected. Similarly, here, okay, these two peaks are connected. Okay, and similarly these two, and likewise you can just extrapolate this discussion, and easily you can make it out. So wherever you see a peak, the peaks, you just try to connect it. Here also the same thing. This peak, there is a carbon, and this carbon is connected to this, and this is connected to this, right? So this is a straightforward information that we are obtaining. Okay. So with this, I conclude myself. But then the discussion of two-dimensional NMR is a very, very vast subject, and we use, I have learned in my MSc little more than what I have taught you here, because the course is exclusively spectroscopic. But this paper, what you have is the bioorganic chemistry plus and spectroscopy. Both are there. Therefore, the content I cannot discuss fully, as we have to discuss another spectroscopy technique. It doesn't permit me to discuss a little more details about the two-dimensional NMR spectroscopy. But I just wanted, my purpose of doing this one is just to give you a flavor. What is this two-dimension? Okay, two-dimensional NMR spectrum is something different. It is somewhat different from the one-dimensional spectroscopy, which gives you more information than the simple NMR spectrum. Okay, the correlation information can be easily obtained from the same nuclei present in the say in a given molecule, or different nuclei present in the same molecule, etc., etc. Okay, and two-dimensional NMR spectrum representation is somewhat different than the one-dimensional, and this two-dimensional NMR spectrum is generally represented with a contour diagram, which will have a diagonal as well as the half diagonal peaks, and the diagonal peaks are which are generally matching with the simple one-dimensional spectrum of the molecule. Okay, and the half diagonal peaks generally represent the correlation between the nuclei. Okay, so that is the something, and the pulse sequences what are somewhat different. What we use in the case of the two-dimensional NMR spectroscopy, and that is too physical, so I did not touch those aspects with you in detail. Okay, so with this, I conclude my today's lecture. About today's lecture, if you have any doubts, any clarification, you can write to me. But there are a couple of examples I strongly recommend you to go through. There are a couple of examples are given in the William Kemp and also the Celestine book. I suggest all of you to go through simple examples like Ipsenol. I did not give explanation. So just go through that Ipsenol. If you find it difficulty, maybe we can discuss in an elaborate way. So I have left it for you as a assignment. Ipsenol two-dimensional spectrum. You try to understand. Okay. Anyway, I'll be sharing this presentation with you. So, or else you can just Google it. That you will get the Ipsenol, and the textbook it is already there. Ipsenol is generally is elaborately discussed. Take your questions, so you can write to me, and I must also tell you that with this we have more or less completed the NMR topic. Okay, many of the things are not there in the syllabus, but still I discussed because I myself felt it very, very important as far as MSc students is concerned. As you are going to attend so many questions, so many the competitive examinations, it is really useful. Therefore, I have taken little more time to explain. Otherwise, since you have already the knowledge of what is NMR, I could have simply taken few examples, few molecular NMR spectrums, and then simply I could have gone and interpreting the data. But that will not serve the purpose. You need to know few more details. That's why I have taken some time to explain the concepts, and few worked out examples we can do it. Not now. Anyway, I have given few things, but a little more problems we can work out after completing the mass spectroscopy. Okay, so that at that time it will be more interesting, and I will give separately the NMR problems, and maybe 2 or 3 classes we will dedicate in solving the problems. I will come up with the spectral data, and you guys you have to work out, and it's a live class itself. We will work out, and similarly the mass spectral interpretation also we will do it after the mass discussion. Then we can combine, we can have problems based on the two techniques. Instead of one technique, based on the two techniques, we can have a detailed discussion, so that that will be even more useful. And sometimes I do, so in an examination point of view, we give the problems not from only the two techniques which I discussed. So I think I remember. So Deepa madam is discussing the IR and UV, right? I think we also couple uh, more than two NMR spectroscopy techniques with IR data or with the UV data. We give problems in the final examination. So with that makes you a complete master uh, in interpreting the spectral data. Is okay. So anything can be asked in the examination point of view, but if you are ready with the one spectroscopy technique, individual spectroscopy techniques, then it is fairly easy to understand and interpret the data. Okay, so the problem is concerned. Already we have worked out few problems, and remaining problems maybe we can take it if the time permits. Okay, I have the plan to take dedicated two or three classes exclusive for one class for NMR, one class for mass spectrum, and then one class for the combined problems. So that I will do only after finishing the mass spectroscopy. In the next class, I will be starting the mass spectroscopy discussion. Okay, so we can have an exam on the NMR spectroscopy. Okay, and the date and time you guys decide, and let me know by Monday. Okay, I prefer to give the time and date for the students, because you only have the timetable of other teacher assignments or other teachers examinations. Therefore, I am giving the choice to you, and you let me know the timing and date, and then accordingly I schedule myself, I prepare myself to give you the question paper. Okay, so on NMR we are going to have one test. Of course, the test can be either Google form, or can be questions will be served to you in the WhatsApp, and you guys have to write the examination, right, and quickly upload the scan copy or the photographs. So that maybe we will decide later, or I will discuss. I will come up on that later on. But you guys let me know first of all the preferred time and date. Accordingly, we will schedule one examination. Okay, bye bye, chalo chalo.